Hello, my name is Thomas Prevenslick. I'm an American living in Hong Kong and Berlin, and the title of this presentation is Simple QED Nanoscale Heat Transfer. Introduction. The history of heat transfer in nanoscale gaps based on the fluctuation dissipation theorem and Retof's fluctuation electrodynamics assumes heat produces temperature fluctuation. This has been going on a long time. Now, the consequences of the temperature fluctuations on gap surfaces is heat transfer by evanescent waves and phonon, temperature-dependent mechanisms. All known theories of nanoscale heat transfer are based on the difference of gap surface temperature. The Planck law of quantum mechanics denies atoms in nanoscale gaps the heat capacity to conserve heat by an increase in temperature. This is in direct contradiction to Retoff. In effect, the Planck law requires theories of nanoscale heat transfer that do not, I emphasize, do not depend on temperature. But all known theories, there may be others I don't know about, but all known theories of nanoscale heat transfer depend on temperature. What this means is there's no valid near-field theories in existence today. How do you do heat transfer without temperature? Some of you may think this is impossible, but it is possible. Heat transfer without temperature precludes the Fourier law of heat conduction, which is temperature dependent. Stefan-Boltzmann law similarly is not applicable. In electrodynamics, indeed, without periodic boundary condition, assumes atoms and nanostructure have temperature, which is clearly invalid. But if you do MD with PBC, what you are in effect doing is extending the computational cell out into the classical regime where temperature does increase. An alternative is to formulate the nanoscale heat transfer based on the Planck law. And I have done that, and I call it simple QED, and that will be the gist of this presentation. A simple QED, heat is conserved by creating temperature-independent electromagnetic waves standing or traveling across the near-field gap. The Planck energy of those waves is E equal hc over 2d, h is Planck's constant, c is the speed of light, and d is the gap dimension. This is the Planck law. On the ordinate, you see the energy of the atom in electron volt, and on the abscissa, the wavelength in micron. Now, you all know this equation. This is the Planck law. If you plot it out at 300 degrees Kelvin, you get the Shell curve, and it goes tangent up here at kT. Now, this white dot is important. It's the point of break between classical physics to the right and quantum mechanics to the left. Now, this white line that goes across is nothing more than a reference, but I included it because I wanted to point out if you're doing nanoscale analysis at wavelengths less than 0.1 microns or 100 nanometers, you can see there's a very big difference between the energy of the atom, wherever this yellow line crosses over here. Virtually, you have to conclude there's really no heat capacity at the nanoscale. And what does this imply? Well, what I've concluded here by simple QED, that heat will be conserved by electromagnetic waves. You can come up with your own interpretation, but it has to be temperature independent. Nanoscale gap confinement. Here's a picture of heat coming in from a hot to a cold body. Now the gap here is nanoscale, dimension D. And here you see a traveling electromagnetic wave. And these vectors pointing inward are momentum. The hot A hot momentum is 3/2 NKTH divided by C. It's coming into the gap, and I show the cold momentum also moving into the gap. The reason that is so is that the temperature of the surfaces of these hot and cold bodies approaches absolute zero because of the Planck law. So any temperatures greater than zero will be driven toward the gap. Now, to summarize this, the gap surface temperatures are absent Brownian motion because the KT heat capacity vanishes, and they're taken as absolute zero. Thermal KT energy of N atoms, and it's arbitrary here, but I've given, as you can see here, it's 3/2 NKTH and 3/2 NKTC. Now again, since TH is greater than zero, and TC is greater than zero, you have a natural inward pointing vector. I sub H and IC are both pointing inward. And this is the momentum, I sub H, U sub H, and similarly I sub C. And the momentum IW of M, traveling electromagnetic waves is given here, M times H over 2D. And the difference between IH and IC is equal to IW, as you can see here. Now the confinement occurs because IW is less than IH and IC, and the heat flow occurs because IH is greater than IC. As an example of simple QED, I'd like to consider white light from graphene. This is an experiment that was conducted around 3 or 4 years ago, and it had a graphene sheet, as you can see, over a trench separated by dimension D. And when they passed the voltage across the graphene, they saw an intense white light come off the graphene, as you see here. Now, to determine the temperature, they used the classical Fourier equation. And the temperature they found was around 1800 degrees Kelvin. And since graphene disintegrates at 2000 Kelvin, it was a reasonable solution. But there's a problem. Bright white light will require higher temperatures, maybe 5000 degrees Kelvin. And simple QED, of course, differs. Graphene remains at ambient temperature when you put a voltage across it. However, the Joule heat is converted to 1.8 keV soft X-rays across the layer, and the 1.8 keV will fluoresce down to around 200 eV, and this 200 eV will basically heat the trench. And you know from this talk, if you put heat into a gap of dimension D, the temperature doesn't increase and you produce waves. Well, simple QED then will produce standing infrared waves. You can see that from the thick heights of the trench E itself. But infrared is invisible. It's not visible, but the overtones in the infrared will produce the white light. So what this example shows is a significant difference between classical physics and quantum mechanics. Now the conclusion, the Planck law shows temperatures in both hot and cold nanoscale gap surfaces do not exist. And evanescent waves and phonons that depend on temperature do not exist at the nanoscale. And only theories of nanoscale heat transfer that do not depend on temperature, may be valid. And the theory of simple QED for standing and traveling electromagnetic waves having wavelength lambda equal 2D is presented and shown to explain white light emission from a Joule heated graphene layer. At least they tend to explain it. And unlike classical physics that conserves heat with an increase in temperature, the Planck law requires conservation by electromagnetic waves. And under any circumstances, classical heat transfer is invalid at the nanoscale. Well, that's all I have. This is my home page. You want to take a look at that. And this URL is a video recording of the presentation you're seeing. Thank you.